Welcome to the Pole Shift News, guys. Good morning from the UK. It's about 7 degrees outside in April. We're on the 11th of April today. And I know some of you are going to say, well, that's not completely uncommon for this time of the year. Occasionally that does happen, but we are in a grand solar minimum. And for that reason, I think it's just as what we'd expect to see. I mean, we have got, even if it's not been reported, some major flooding in the UK as a result of, this prolonged winter. So, we're looking at the structure of the atmosphere, and as promised in the last video, I would have already done this experiment for you guys, but I was lacking one critical component for the experiment that we're going to do, and you're going to see that later on in this video, and that is we're going to test the atmospheric oxygen levels so that we can get an idea as to how much oxygen is in the reservoir and whether it's changed over a period of time. You can see the major constituents of dry air by volume on this chart that I'm showing you. That oxygen is around 209,000.4 parts per million, which constitutes around 20% of our atmosphere. That is unless you start going above 33,000 feet, as you can see, or 10,000 meters, in altitude. It will change the composition, and that's due to the atmospheric layers of gases, some being heavier than others, and the higher you go, that composition changes. So, the reason why I mentioned the parts per million, first of all, is if you go on to null school and you're looking at let's say the sulfur content caused by volcanic eruptions, you're going to be able to get some idea as to how much that is and whether it's a significant matter. But just for argument's sake, look at carbon dioxide on this chart. We can see 0.04% of our atmosphere, and yet they claim that this is one of the major contributions of greenhouse gases which causes global warming. But it's taken up a very small part of our atmosphere. Another greenhouse gas you might not be familiar about is water vapour. And that's because it's a tri-molecule just like CO2 is. And the reason for this is because they're both tri-molecules. Just a little bit about valencies. Now, valence is the actual amount of bonding sites that an atom like oxygen has, and it's got a valence of 2. Carbon's got a valence of 4, which means that there's 4 active regions that it can bond to, but as oxygen has 2, it does a double bond. So you've got oxygen, 2 oxygen molecules in the CO2, both with a double bond, so it satisfies both the oxygen double bond site and the carbon 4 bonded sites, and you get a double bond with each oxygen. On the hydrogen, on the H2O, a little bit different, but because hydrogen's got a valency of 1 and oxygen has again a valency of 2, it captures 2 hydrogen molecules with its double bond, the oxygen does. So, okay, let's get on with the experiment, and I'll explain why we've chosen the route we have. Now, remember, we don't have the luxury of a gas analyzer, because if we did, we'd just flick on the button and it would take a sample of air and tell us that it's got whatever percentage in the air of oxygen, as well as nitrogen and other things. So what we have to do, as we haven't got the the gas analyzer, is we have to use a little bit of chemistry here, and I explained briefly what that was, but I'll do now. I'll go and get the camera out and I'll show you what we've got set up, and I'll explain how we're doing it. And this is something easily you could create back at home if you wanted to compare the results of my experiment, or just at any point in time you want to check how much oxygen is in the atmosphere. The reason why we're interested in doing this, and again, I think it's really important. First of all, oxygen to us is majorly important. Without oxygen, we're going to not live on this planet very long. So, it's a great fact that we've got oxygen. The other thing is, many millions of years ago, the atmosphere was a concentration of CO2. It wasn't until, the scrubbing by this zooplankton in the oceans and other microorganisms that thrive on oxygen had stripped all that CO2 out of the atmosphere, and as a byproduct put oxygen into the atmosphere, and that allowed us, as some people would say, allowed creatures to crawl out of the sea and then, begin to develop breathing as there was an oxygen, surplus in the atmosphere. And but the point is, the reason why we're going to do this experiment is because today there has never been so many people on the planet. There's never probably been so many animals on the planet as well. We do intensively rear cattle now to sustain the amounts of people on this planet. If you ask me, I think we are definitely in the red. If we was in a car looking at the RPMs, we would definitely be in the red with the way we're trying to keep up with the production of everything else. I mean, we're trying to sustain right now 7 billion people on this planet, and as a result of that, we are consuming, I would say, a hell of a lot of oxygen. Not just with animals that breathe oxygen, but also with the industry that requires the oxygen in order to, keep engines running, keep ships running, keep jet aircraft in the air. We consume a hell of a lot of oxygen. It's one of the important gases on our planet, and generally it is in our atmosphere around a volume of 20%. So, it just sometimes makes me wonder, whether we have tipped the balance of oxygen on this planet. And if that is the case, then, the alarm bells should start ringing for all of us, because we are definitely doing something we shouldn't be. And that's just putting one thing on the side. Just think about what we're doing in the rainforest. These are the lungs of our planet, and we're deforesting it. And, that rainforest produces a hell of a lot of oxygen for us. So if we're not only consuming a lot of oxygen, but we're also cutting the root source of the oxygen, then, yeah, we're not very intelligent, for one. But, at some point, it's going to reach critical levels. And, it's for that reason we're doing this important experiment. On this channel, we are covering, as far as I'm concerned, the important aspects of, things that can affect us. If there's a depletion in the oxygen levels, then that's a big problem. If the Earth goes through a magnetic reversal, and the magnetosphere collapses during that reversal, that's a big, big problem. And not only that, even during this point in time where the magnetosphere is weakened 20%, if we are experiencing similar scenarios to what happened to Mars, where sputtering is taking place and the atmospheric oxygen is being stripped away from, let's say, the mid-Atlantic anomaly region, then, we need to address the problem. We need to understand, first of all, if it's a problem. If it is, then we need to do something about it, and we need to prepare. Because, we do have, equipment now on this Earth that can produce, ampoules for, let's say, oxygen. For instance, we've got these machines now in submarines. They don't have to keep resurfacing to flush out the stale air in them. They can reproduce their own oxygen for pretty much 6-7 months or even longer periods of time. So, we can do something about this at least. But if the magnetosphere collapses and, as a result does strip the oxygen out of the atmosphere, then, it's a different ball game, because it just doesn't affect oxygen. It affects a lot of other things. Really, our main single most things on this planet, that we should be alarmed about is the magnetosphere and any changes to the magnetosphere. Let's do this experiment anyhow. If you want to recreate this experiment yourselves to find out how much atmospheric oxygen is in the atmosphere, all you're going to need is a few things: some steel wool, some water, and some household vinegar. Because it's acidic, it will create a rusting or oxidation on the steel wool. What else you're going to need is a graduated tube with a small hole in it, and you can see, if I just zoom in there, on the level of the 10 you can see I've drilled a tiny little hole in the glass, and that is so that when I place it into the water, it will give me no more than 100 or 10 mils of atmospheric air in there.
Now you can see it's already risen almost up to the 9 point. This is measured in graduations of 20%, so at 8, if this water vacuum sucks up to the 8, we know there's 20% oxygen still in the atmosphere. In total, there's 100 mils of atmospheric air in there. What we've done is we've placed a little bit of the steel wool, which has been soaked in a bit of the household vinegar at the top, and you can see already the oxidation's taking place because of the discoloration of the steel wool. It was nice and shiny when we started, and we know that the oxidation's taking place because of it's going orange, or it's rusting. And what that'll do is that will consume, through this process of mixing the vinegar with the steel wool, it will consume all the oxygen out of these 10 mils of atmospheric air. And when it does that, it will stop. If there's 20% atmospheric air in our atmosphere, it will stop at the level of 8 in this vessel inside. We can see that we're already 10% oxygen that has been consumed through the chemical reaction of mixing the vinegar with the steel wool. What's happening is it's drawing out all that oxygen in this tube, and it's placing it in the still in the chemical reaction. So yeah, we'll come back in a little bit. We've got another 10%. Let's hope that there is another 10% of oxygen in our atmosphere, and we'll see how we're getting on. What will happen is that in the outside chamber where the water is, it will drop the level, and through the consumption of oxygen in the inner tube, it will draw up the water through this little hole that I've put in the glass on the inside vessel. So we will end up with whatever amount of oxygen is in our atmosphere, and you should be able to see for yourselves. But it's not a difficult experiment to recreate back at home. You have got to make sure that you get that drill hole exactly, or as close as, to the level of the 10, so that you don't have any more than 100 mils of atmospheric air in the tube. So that takes a little bit of getting used to. You might have to drill a couple of holes a few times, and it's not easy when you're drilling glass. So yeah, we'll come back in a little bit and we'll see how we're going. You can see even with this mild acid, the vinegar, that the reaction's taking place quite quickly, really, on the scale of things. I mean, we could have put nitric acid on there and it would have zumped the the oxygen straight out of there in the process of oxidation, but we don't have those exotic acids. But what we do have is what most of us have got, is household vinegar, and it does work. So we'll come back in a little bit and see how much further the water does rise in the inner pipette. The experiment has been going on now for around 2 hours. You can see that the water has risen up to the 12 mark on here, which would mean there is 8% missing of the oxygen in this first run of this experiment. So I don't think there's any more reaction going to take place at this point, but I'm going to give it a little extra time just in case it does. There's plenty of vinegar on the steel wool, and you can see there's still some shiny steel wool there, so there's plenty of oxidation that can take place. But early indications are showing that there's 12% oxygen in the atmosphere. That was at least in this tube. Now, we're not at any great altitudes, and I will show you a chart where oxygen starts to affect athletes at different altitudes, and we're at about 500 feet here in the central England, above sea level. So the percentage of oxygen should be somewhere between 21% and 19.6% on this chart. We'll see. Like I say, early indications is showing 12%, and that's a very large amount of oxygen that's missing in our atmosphere, especially if it's supposed to be between 20 and 21%. But then It wouldn't surprise me if that was accurate, but what would surprise me is how nobody, if this is the case, is not noticing the effects of 8% reduction in the oxygen in the atmosphere. So what I'll do, I think, here is I'll give this experiment another 4 hours as it is. I'll measure any changes, record them for you so you can see for yourself, and then I'll repeat the experiment another 2 or 3 times. If we keep coming back with the oxygen levels at what they are, then it is what it is, guys.
So guys, as you can see from the chart, where my location is in central England, I'm around about 500 feet. So, you know, the reading we've got back is something very different. It's saying that the altitude category is very high. You know, 12%, it's very high. And it doesn't ring right to me. So, you know, I'm going to let this experiment run for another few hours, and then I'm going to redo the experiment another 2 or 3 times. If it keeps coming back at 12%, then, you know, it is what it is. It's 12%. I have conducted this experiment before, probably around about 4 years ago, and got a different result. We achieved normal levels of oxygen in the atmosphere with the same experiment. So, has something changed in the last 4 years? If so, you know, what has led to the change in reduction in oxygen in the atmosphere? But before we go down that road, let's just confirm our results and see if we get the same results. If it keeps coming back 12%, then, you know, something's dramatically changed. I mean, we're talking like 8% of oxygen missing out the atmosphere at this level. And if that's happened, then where's the oxygen going? So I'm going to leave the video here, guys. I'm going to remind you that, you know, we are an observatory. We conduct, you know, I would say, reasonable quality research here. You know, we're not funded by any government organisation or by any corporate organisation. Therefore, nobody influences what we do on this channel. You know, it's recorded, and you see what I see. Just like in this experiment today, you know, when we get the results of the atmospheric, of the magnetosphere depletion, you know, if there is any, you will see it. If the magnetic pole migrates, you get that data as well. You know, like I say, we are not just a YouTube channel. We provide information on the website, as well as collect the data ourselves. We've done a lot, guys, over these years to deliver, you know, a truthful based platform where, you know, we get to find out what really is going on. So with that, I'll mention there's a link down there if you want to support it. Thanks for that, and I'll say what I usually do, guys. Enjoy the rest of your week. Over the next few days, I'll have some more repeated experiments of the atmospheric oxygen. Hopefully, you know, one way or another, we know where we stand with that. And I'll say what I usually do. Bye for now.